Hello and welcome. In a previous video, I used a tool to help visualize binary numbers and some of the arithmetic operations. Today, I go over the full tool. I'll also talk about some of the things the tool taught me about the 6809 operations I didn't know about. I'll also go over some of the code so you can see how it works. And you too can download it. It will provide decades of family fun. All right, let's go, and it's time for Coco Town. This is what it looks like when you first run the tool. You can use the arrow keys to cursor around this header row, which controls the input to the operation. So we start off highlighting the signed decimal, and I can go right and I can go left, including over each individual bit. When I'm over something I want to change, I can use A and Z to increment or decrement. So I can use A to go up one at a time, Z to go down one at a time, and I can individually flip each bit either up or down, all up, all down. I can also use the S and the X keys to very quickly go up or down, and it will continue to go up and down while I'm holding the key down, whereas A and Z only go up one at a time. On the first screen, you'll see we get the results of the COM and the neg instruction, which updates itself whenever the A changes. And we also get to see the result of these condition codes. Different screens will have different condition codes depending on what's relevant, although not all the condition codes that are shown are relevant to each operation. But these do reflect the actual bits in the condition code register as they were immediately after that operation was finished. Hitting the spacebar moves us to the next screen. So the next screen is all about all of the left side rotations, and then hitting space again, we get to the right side rotations. The next screen does addition, subtraction, multiplication, and sign extension. And finally, the binary coded decimal screen. So assuming you've set up A and B to be proper binary coded decimal numbers, you get to see the result of just a raw addition, and then the result of a raw addition plus the decimal adjust. And by the way, in an upcoming video, I will be talking all about binary coded decimal. So if this intrigues you, hold on to your seat. I'm going to go over the code in a minute, but first I just wanted to point out a couple things that I learned, either because I was working on the tool or just plain using the tool. On the rotation left screen, it does 3 rotations in a row using either the roll, the lizzle, or the azzle. And you start cycling through the numbers, it seems like you always get exactly the same response in both. Same condition codes, same result. And part of the reason for that is that lizzle and azzle are the same thing. They're just synonyms for the exact same instruction. In fact, it looks like the opcode byte is simply 48 for both. We can start to see a difference with roll if we go low enough. So at this point, everything is the same, but if my starting point is -128, so I now have a 1 in this section here and zeros elsewhere. Although the result of the first rotation is the same, the next one and the one after that are different. All of them will rotate the leftmost bit into the carry bit, but only the roll will take the carry bit and rotate it into the least significant bit. Lizzle and azzle will just always put 0 into the least significant bit regardless of what was in carry. And that's why you see this 1 disappear here as it goes into the carry, and then reappear here as it then gets cycled back into the least significant bit. Whereas lizzle and azzle are just all zeros. On the rotate right screen, things are a bit more interesting. As before, all the different rotations rotate into the carry bit. And since we're going right, it's the least significant bit, bit 0, that gets rotated into the carry bit. Boom, boom, boom. And also, as before, it's only the roars which will rotate from the carry bit into the number, in this case into the high bit, bit 7. The Lizra and the Azra again mirror each other's behavior, and they continue to mirror each other's behavior for quite a while. When our starting byte is at 127, they're doing exactly the same thing. They're rotating all those ones to the right, filling in the rest here with zeros, rotating those ones into the carry bits. But when our upper bit is 1, then we reveal a difference between the Lizra and the Azra. Azra does no longer rotate a 0 into the high bit. Instead, it rotates the high bit into the high bit. It's doing this to preserve the sign. So if you wanted to divide by 2 and you had a signed number and it happened to be negative, it will remain negative after that division. But as Darren Atkinson warns us, it's not quite the same as a division by 2 when the value is negative, because it will round in the wrong direction. What happens when we do -5? -5 divided by 2 is apparently -3. Darren Atkinson says it should be -2, but Azra will give us -3. I'm not entirely sure that's wrong, though. It is true that a +5 shifted right, thus divided by 2, gives you a 2 and not a 3. But in both cases, it's rounding down. So it might not be what people expect or what they need or what's convenient, but it is consistently rounding down whether or not you have a positive or a negative number that you're shifting. Don't even tell me this isn't interesting. This is freaking cool. And something I learned on this page about the multiply operation. If I've got a 5 and I've got a 2 and I multiply them together, I get a beautiful 10. And remember, when I do the result of a mul instruction, I get a full 16-bit number. What happens when I do negative numbers? Bloop, bloop, bloop. 5 times -1 is positive 1,275. What? But sure enough, the mul operation only does unsigned muls. And Darren Atkinson very explicitly tells us we take the unsigned 8-bit in A and the unsigned 8-bit in B, and then we get the unsigned result in D. So if we go back here and instead we look at our unsigned values, 5 times 255 is what's going on, folks. And sure enough, that is 1,275. So how does all this work? The code is separated into 2 pieces. First is the piece that's common to all the screens. The common part is you'll always have an A with its binary and its decimal representations, and you may or may not have a B as well. And so you still need the arrow keys to respond and to highlight the appropriate thing. You still need A and Z to go up or down by 1. You still need S and X to go up or down by as long as you're holding it. So that common stuff is in one place. And then the things that are custom on each of the screens is separate. The separation of functionality is handled by a page info struct. So we have one of these page info structs per screen of the program. This encapsulates all of the custom things that need to happen for each screen, and doesn't do any of the common stuff. So each of the screens has its own initialization routine, its own update routine, and it chooses where the A register will appear up in the header and whether or not a B register appears, and if so, where that would be. And the array of page info structs looks like this. So for example, on the very first page where all we have is a com and a neg, so we're only using A would appear at that location, and we have a 0 for B that shows it doesn't appear on the screen at all. And we have our custom routines to initialize and to update that screen. Then we have the rotation left, the rotation right, the arithmetic page with addition, subtraction, and multiplication, and finally the binary coded decimal. And in both of these cases, we have both an A and a B register. So the main loop iterates each time we change the screen, in which case we run that screen's initialization routine, and then we start the page loop. So as long as that screen remains active, the page loop keeps on iterating. We update the screen, and this will contain both elements that are common and calling the custom subroutine. We render the cursor, we poll the keyboard and respond, And depending on the result of the keyboard, either we're going to go to the next page, or we're just going to go back up to the page loop. So as one example, let's take a look at the update screen routine. The part that all of the screens share in common is this code which figures out where A needs to be printed, loads the A register with the in-memory variable of A, and prints it. Then checks whether B needs to be printed. If not, we skip. Otherwise, we load the A register with the memory location for B, and we write B. And this write byte includes splitting it up into binary bits and showing the signed and the unsigned forms. When that's done, then we jump to that particular screen's custom update screen routine. So this would be responsible, for example, for calling com or neg, or calling add, subtract, multiply, whatever are the custom operations on that screen. For example, the update screen routine for the com neg screen is pretty simple. So to write the result of the com instruction, we get the value of A, we actually run the com instruction, we preserve the value of the condition code register. All this does is it transfers the condition code register into the B register, and then stores B into this now is the memory location where I'm storing CC. So CC is merely one of these memory locations where I'm persisting the value. As I'm looking at this now, I wonder maybe I could just have done a transfer, a TFR instruction from CC to B. Looking at the transfer instruction, it does look like the TFR will not affect the condition code register, unless obviously the condition code register is the destination that will affect it. So I guess I could have done a transfer, but I'm not changing it now, because I don't care. We definitely don't need to be super fast. So coming back after the com instruction and after we have preserved the condition code register, we go ahead and write the result, and we write the values of the NZVC bits from the CC location that we just tucked it away in. And something similar for neg, and something similar for pretty much every other operation you saw. Back into the main loop, one of the other interesting parts is how we pull for the keyboard. If you saw this video, you saw some of the advantages and disadvantages of polecat. I wanted to have my cake and eat it too, so I am both using polecat and not using polecat. For most every key, I'm just using polecat because it does very nice deduping for me. It will avoid the user accidentally double pressing something they didn't want to double press. But the S and the X keys, I really do want to cycle very quickly through the ranges, and I want you to be able to hold them down and have it continue to cycle through. So before I call polecat, I call this custom keyboard routine. Pol and exec fast keys is just about the S and the X. First up, keyboard polling is so darn fast, I even have to slow it down. I have this delay factor, which I seed with this number, hex 40. And what that means is the first hex 40 times this routine is called, it does nothing. It just returns. And then every hex 40 times this is called, will we actually do something? So we'll pull for S, we'll pull for X, and if either of those are true, then we'll run the code in response to the S and the X. And the way we pull for a letter is we pick the column bit vector that key lives in. We store that into the PIA, then we read out the response. And then we ask if there is a 0 in the row vector where that key lives. And if so, we're good. Otherwise, we pull for X doing the same thing. And if we found X, we're good. Otherwise, we just return nothing. And in response to the call, we immediately look at the condition code. If we had loaded the A register with either the S or the X, this would be not equal, and we would execute that keystroke. Otherwise, we will have cleared the A register, and condition code 0 will be set, and so we'll just fall through and call polecat. And in either case, we have the same routine that we call here to execute whatever keystroke that we sensed. Execute keystroke simply looks at this array, where each element is a key code followed by a routine. So we have entries for left, right, up, down, A, Z, S, X, spacebar, and the question mark. So we just go through the array looking for a match and then jump to the routine we found if we found a match. And that's about as much of the code as I can tolerate going over. You're welcome to look at the rest on your own. Check out the link in the description where you can download and play with it for yourself. One thing I will say is that having each page represented by its own page info struct made it really easy to add new pages. Once I had the first couple in here, and at that point I had refined what the common code should be, it ended up being very quick to add the arithmetic page, And I wasn't even planning to do a binary coded decimal page until later I decided, I want to do a binary coded decimal page. And again, adding this ended up being quite quick. To be frank, this did require some changes to the common code, and you'll see more about that in an upcoming video. But even so, it was pretty quick to add this. So now it's your turn. I encourage you to check out the description, click on the link, and try this out for yourself, look through the code, and find all the bugs that I left for you. There are no bugs that I know of, but that doesn't mean there are no bugs. As always, thank you for watching.